Hi everyone. In this presentation, I'm going to introduce our work of a comparative study of nonlinear NPC and differential flatness-based controller for quadrotor agile flight. Accurate trajectory tracking is essential for many applications of drones, such as fast search and rescue operations that requires avoiding obstacles and flying through narrow spaces. However, it is very challenging to accurately track a trajectory in agile flights. In this study, we systematically compare and enhance the nonlinear NPC and the differential flatness-based controller. They are the two mainstream control architectures for quadrotor agile flights. The NMPC solves a nonlinear programming problem online to find an optimal trajectory with minimum error from a set of points on the reference trajectory. Its predictive nature and ability to deal with input constraints make it suitable for tracking highly agile trajectories. On the other hand, the DFBC tracks a single point on the reference trajectory by utilizing the flatness property of quadrotors. It converts 3D position and its derivatives to quadrotor states and input references, which is used by a proportional controller. As the original DFBC does not deal with input constraints, we also improve DFBC by using a tilt-prioritized attitude controller and a quadratic programming-based control allocator. This can effectively improve its performance to address rotor thrust limits. We initially compared the NMPC and the modified DFBC in tracking over 100 agile trajectories in the simulation. These trajectories were divided into two groups based on their dynamical feasibility, where dynamically infeasible trajectories cannot be perfectly tracked due to the thrust limitations of each propeller. These trajectories have different maximum accelerations up to 6g, they have different shapes, and different maximum velocities up to 20 meters per second. The two plots on the right show the position tracking arrow of trajectories with different maximum accelerations. We observe a comparable tracking accuracy between the two methods for dynamical feasible trajectories. However, NMPC significantly outperforms DFBC in tracking dynamically infeasible trajectories, even though our DFBC implementation includes a quadratic programming allocator to address actuator saturations. We further assessed the robustness of both methods against various uncertainties, such as drag, mass, center of gravity bias, rotor coefficients, external forces and moments, and system latency. We observed that NMPC is more robust to rotational dynamic uncertainties. On the other hand, DFBC is more robust against force disturbances and large system latency. We also compared their computational efficiency on an NVIDIA Jetson TX2 embedded computer. We observed that NMPC has an average 3 milliseconds CPU time, and DFBC is significantly faster with only 20 microseconds to generate per control command. To account for model uncertainties in real-world experiments, we have improved both methods by hybridizing them with an incremental nonlinear dynamic inversion controller to handle model uncertainties. INDI leverages incremental nonlinear model, which uses sensor measurements to replace a major part of the original nonlinear model. Then it performs dynamic inversion on the incremental model to obtain control inputs. Hence, the majority part of the model uncertainties can be directly captured by instantaneous sensor measurements and addressed by the controller. We propose to use the commanded angular acceleration from NMPC and DFBC as the virtual control input of the dynamic inversion. Since both controllers consider the thrust limit of each rotor, they can provide a much more feasible virtual control input for dynamic inversion compared with traditional PD controller. We have validated the proposed NMPC INDI and DFBC INDI algorithm through multiple real-world experimental trajectories, ranging from simple looping trajectories to complex racing trajectories with top velocities of up to 20 meters per second. Our results show that NMPC and DFBC with the INDI low-level controller have comparable performance in tracking physically feasible trajectories. and hybridizing with a robust low-level controller such as INDI can remarkably improve the tracking performance of both controllers. And such improvement is also significantly higher than simply adding a drag model. Thank you for your interest in this work. Please check our paper for more details.